All right, our next speaker is Sean Welek from, he's an assistant professor at Carnegie Mellon, and he gave a very nice tutorial yesterday on how you can use language models for mathematical reasoning, and he has more depth and details here. And today I'm going to be a little bit more strict in managing time because we have a very packed schedule, and yesterday was unstructured and maybe more free-spirited, but I'll not sell you short here.
Okay, thanks. So thanks for the invitation to give a talk, and really excited to tell you about scaling laws of formal reasoning. So a lot of us have become familiar with these large language models, so through systems like ChatGPT, and these are based on a type of foundation model, and they kind of give you this general platform for sequence generation. So you can do anything from summarizing a document by giving it to ChatGPT. You could even do things with images, like give it a screenshot and have it generate you some code. And essentially, anything that you could think of that can be framed as a kind of sequence-to-sequence task is kind of eligible for a system like this. And really, the underlying idea is you collect this massive, diverse data set, and then you train a generative model, so a language model based on transformers, and then you somehow adapt it to tasks. So you either keep training the model further, you can prompt it in various ways, and if you've used something like ChatGPT, you're probably familiar with this process. So there's a question of to what degree systems like language models will have an impact in more specialized domains. So things like finance, things like medicine, science, and the one I'll focus on today is mathematics. And in these expert domains, we have kind of unique domain knowledge that may or may not be captured by the model. You also have really high demands on things like correctness and reliability. And so it's kind of an interesting question, whether these models can do anything useful. So luckily, we've started to see some promising use of language models in mathematics. So there's a really nice seminar hosted by Michael Douglas at Harvard called CMSA. And so you can check out some various talks from there, but this could vary from things like helping to generate verified proofs in a formal system to just helping solve some types of problems that you could frame as kind of text tasks. And then if you've used something like ChatGPT, you could imagine having just open-ended conversations with the model, maybe having it help you learn or use math. So to be concrete, here's kind of two different problems that we're going to have in mind in today's talk. So first, here is a solution from a model that I'll talk about called Lemma. And it's on a common benchmark. The name's kind of unfortunate. It's called the math benchmark. So anytime you say you're working on math, it's kind of an overloaded term. But basically, the model's just solving this mathematical problem as just text generation. So these are just tokens of LaTeX, and then at the end, we can check the answer. And this one turns out to be correct. Of course, you don't have guarantees on whether the intermediate steps are correct, or if the answers are going to be correct 100% of the time. Looks like I need to fix this Zoom a bit. Sorry about that. So another one that I talked about a lot yesterday is doing formal mathematics. So here the math is represented as source code. And so instead of just treating it as a text generation task, like on the top, where we have a problem and then write some solution in LaTeX, you can actually write a theorem in one of these specialized languages. So the one on the left is called Isabelle. The one on the right is called Lean. And then the nice thing is, if you produce a proof in these languages, then you can check it with the system. Essentially, you try to compile the code. And if the code compiles, then you know that it's guaranteed to be a correct proof of this theorem. And so, yeah, increasingly these are starting to have more and more of an intersection with mathematics. For instance, Terence Tao had a kind of famous, he started getting interested in these and had a few side projects in late last year. And it resulted in him, with some others, formalizing a result in one of his recent papers. So you could essentially have a formally checkable version of the result in the paper. And yesterday I gave some more examples of the intersection of formal mathematics with both math and machine learning. And so the theme of today's talk is about scaling laws. So what are scaling laws? So scaling laws give us some predictable relationship for some quantities. And so with language models, the really cool result was that if we just increase compute at sort of pre-training time, then this actually gives us very predictable improvements in the model's language modeling performance. So what do I mean by compute? You could basically increase compute in two different ways. You can increase the number of tokens that the data is trained on, so that's in the middle. And or you can increase the number of parameters in the model, so make the model larger and larger. And then if you look at the model's test loss on the kind of data set it's being trained on, you can see here that it's kind of predictably getting better. So then there's a natural question which comes up, which is like, does this apply to everything? Can we actually come up with some kind of predictable improvements for actual downstream tasks, like solving problems or generating proofs or things like that? So today, I'll talk about two different themes. The first is when we go to pre-train the model. It turns out that in mathematics, the quality of the data matters just as much as the quantity. So if you just train on kind of general domain data, we'll see that it actually doesn't do as well as if we can, actually create high quality data for math specifically. And then second, I'll talk about after the model has been trained, how we can then scale compute at inference time. So here we frame this as the problem of learning a really strong evaluation model, and then you can basically scale up the amount of samples that you take from the model, and then choose one with your evaluation model. So the first part is based on this paper called Lemma, which we'll be presenting at ICLR, and it was led by Jahangir, who's a student at Princeton University. And so before we saw this nice plot, and it suggests this kind of initial approach, which is, what if we just train a really good generalist model? So specifically, like, what if we make our data set so big and just ensure that some math is in there, and then just keep scaling up the size of the data and keep training a larger and larger model and see what happens. So these are really expensive experiments to run. So we could just look at what some others have done. So this is a model from Meta, and actually the smallest one that they trained was 7 billion parameters. And they trained the model on 2 trillion tokens of data. And this is kind of general domain data in the sense that like it could come from web pages, from GitHub code, from Wikipedia. And so this is showing on the x-axis how much compute is actually used to pre-train the model. And the blue dot right there is the Llama model that I just mentioned. And then on the y-axis is the accuracy on this math benchmark. And you can see that even after spending all this compute on that 7 billion parameter model, the y-axis actually doesn't even go up to 100. It only goes up to 25. So it's very far from even solving these types of problems. Then what you could do is add even more compute. So this CodeLlama model, you could go up to like a 34 billion parameter model, which is trained on even more data. And again, it's improving, but it's still less than 15%. And in particular, it's actually much worse than these red lines, which are language models that have been specifically adapted to mathematical data. So the first kind of major large language model to do this was called Minerva from Google. And it basically shows that, while training a generalist might be possible, it's probably not the most efficient way to learn how to perform well in an expert domain. So what we looked into is basically, building on the Minerva recipe and expanding it to informal math, formal math, and math-related code. And so the goal here was to take a generalist model like CodeLlama and then construct a really high quality and diverse math-related corpus, which we called the proof pile 2. So compared to the pre-training data set, which has trillions of tokens, the proof pile 2 ended up having around 50 billion tokens. And then what we can do is just keep pre-training the model on the proof pile 2. And then this gives you a new base model or foundation model. And again, it's a foundation model in the sense that you can still then go and fine-tune it. You can still prompt it and use it for a wide variety of tasks. Now those tasks are kind of in the domain of math. And so now, after doing this, we see this large jump in performance. And here, again, we're just prompting the model, so it wasn't trained specifically for this task. And when you compare the amount of compute that's used for pre-training versus this kind of mathematical domain adaptation, the domain adaptation is actually a much smaller amount of compute. So yeah, you can see this jump in performance. And now even our 7 billion model is doing better than the 34 billion. So clearly here the key is high quality data. So as I mentioned, the proof pile has about 50 billion tokens in 3 different subsets. We collected a code subset called the algebraic stack. The first author, Jahangir, has a math background, and it's a kind of mathematical pun. And so we get code from GitHub from another data set called the stack, and then we specifically extract formal proof states and put those into the corpus. And so for more details on that, you can check out yesterday's tutorial materials. And then the other key thing is basically filtering all of Common Crawl, so trying to get as much math-related web data as possible. And so this was actually part of a separate project called Open Web Math, where, yeah, Common Crawl was basically filtered with these 6 different stages. One of them was kind of a learned model, which said, given this document, how likely is it to contain some math-related data? And so you can see here that you go from this massive number of pages on the web to about 6 million documents of math-related data. So again, you can test the model by prompting it on various benchmarks. At the time of doing this, this Minerva model was really the only kind of math-related foundation large language model. And we were able to kind of match or outperform it. Another cool thing is that we showed that you can just prompt the model to do this formal theorem proving. And in particular, it kind of improved over the baseline starting point and had similar performance to models that were kind of specifically tuned for the task. And then again, in yesterday's tutorial, I gave some more examples of further adapting these kind of models for theorem proving. Then a cool thing you could ask is, like, how is this model actually kind of useful in practice? So another thing we did is build a tool for integrating the model into the Lean Proof Assistant. So you can essentially take one of these libraries which efficiently runs a large language model on your laptop, or call out to one of these LLM APIs, and then basically communicate with it in the Proof Assistant, and get things like next step suggestions. So yeah, we had We had a paper on this at NeurIPS workshop. There's also been some really other cool tools built by other groups. One of them is called Lean Copilot. And so we're starting to see language models actually, like being useful in these proof assistants. So here's an example of, this was actually running on my laptop, using Lemma to kind of suggest the next step in this, in this proof. So yeah, in the first part, I talked about a lemma, which is this recipe for specializing a language model to math. And by focusing on the data quality, we could basically enable more efficient scaling. And then next, I want to talk about, after we kind of run out of human data, how might we go beyond that? So this is based on a paper called Easy to Hard Generalization. And it was led by Zhiqing and Long Hui. So here the idea is that eventually we might actually run out of data. And so we kind of have to move to this setting where humans can provide supervision or data on easy tasks. And then we want our model to generalize to harder tasks. And so we operationalize this using this math data set that I mentioned, where we train on the easy problems, so level 1 through 3, and then test on the hard ones, levels 4 through 5. And the key idea that we want to explore is that oftentimes evaluating a solution is easier than generating a solution. And so on the left hand here, you could imagine that your generator might succeed on easy problems, but then fail on hard ones. Whereas maybe there's some hope of actually training an evaluation model only on easy problems and having it be able to generalize to evaluating slightly harder problems. If we're able to do that, then you could kind of come up with a natural strategy where you sample a lot of potential solutions from your generator, and then you kind of filter them with your evaluator, and then get some level of generalization to the hard problems. So that's kind of the goal, and it's what we experimented with. So what we did is wanted to train an evaluation model only on easy problems, and then use the evaluator to select generated solutions on hard ones. Then the way we train the evaluator is to predict both the correctness of a solution, so this is kind of an outcome-based model, as well as predict the correctness of intermediate steps. And you can basically have, there's some data sets of humans annotating the correctness of steps or solutions. And then at inference time, we generate up to, say, 1,000 solutions, and then do this weighted voting technique using the evaluation model, where we basically score each solution and then choose an answer group with the highest score. And so what we can see here is that using the evaluator on harder problems in this weighted majority scheme actually leads to much better generalization on these hard problems. So in particular, on the x-axis is showing if we just keep sampling outputs from the model, then you could kind of take the answer with the most votes. You could just choose the best one using your evaluator, or you could do this weighted evaluation. And it's kind of cool that as you scale up the number of samples, these methods start to show differences. This also translates to better performance on all tasks. And yeah, one cool result is that with the lemma model, which is based on all openly available components, if you add in this inference time re-ranking, then you can actually roughly match the performance of these closed models on this math task. And then finally, you can imagine using this evaluation model to actually improve the generator through reinforcement learning. So here we generate solutions on both easy and hard problems. and then you use the evaluation model as a kind of reward function for reinforcement learning. And the cool result here is that by doing this reinforcement learning, you can actually do better than if you just fine-tune on both easy and hard problems. So yeah, I think there's a lot more to explore in this direction. So today I talked about two different aspects of scaling, one related to the data quality, and the other to inference time scaling and scaling up evaluation. And so looking ahead, I think there's a lot of exciting directions based on this. The first is that I showed this image of filtering Common Crawl, and there's kind of no reason that the first pass of it was the ideal algorithm. And so in general, I think what we're going to see is better and better data algorithms for kind of mining data for a particular domain. And then the other big open question is whether we can just generate data with these models and have some kind of synthetic data. And then the question is, yeah, how do models scale as we just generate more and more data? And then second, this 0-1 correctness is kind of nice. But even in these mathematical tasks, there's things that go beyond just these clearly defined metrics. And so how we kind of enable this automated evaluation for these more fuzzy things is kind of an active area and an open question. And then how we use those to ultimately improve systems so that they can, go off and discover new knowledge and keep improving over time is kind of the eventual goal. So both of these projects were, of course, part of collaborations with amazing collaborators. Here's some links to the code, and yeah, I'm happy to take questions.
Yeah, thank you very much. You brought us back on time. All right, questions from the audience? Mic can be passed on here. Can you pass me that mic? Yeah, I can get this. Yeah. All right, Jean-Luc.
Two questions. Can you explain a bit about this case where you had multiple solutions to the problem, many solutions? I mean, are you looking at the solution like approaches to solving the problem? Because most of the math problems would have a unique solution, basically, if you try to prove something. And the second point is that it seems that, if you change the data and then focus on math-specific database, what does that mean exactly? That you should filter the quality of the journals or something like that, or avoid the physicists because they're very loose with math? Or
yeah, so both things are really good questions. So the first was about the multiple solutions, and the second was about data. So yeah, as for the multiple solutions, here we're in a setting where you have an answer at the end. And so what we're doing is sampling, say 1,000 different solutions. And then many of those different solutions will kind of end at the same answer. And then we're weighting each answer set and then just take one from the answer set with the highest weight. And so, yeah, in this case, we're not really differentiating between the particular solutions. I think one area where that becomes really interesting is in the formal theorem proving, because if you look at the way that some of the formal proofs are written by humans, they're often made really short and compact. And this is good for things like making sure that your code base doesn't grow too big, but then they're not necessarily good for resembling the kind of natural chain of thought that a human would have or something. So, and then about the data, so one thing is trying to define even what a domain means is still not clear. So here, the data kind of intuitively seems to resemble mathematical data, and it actually ends up including things like physics articles, because when we filter the data, it's based on a classifier that detects whether LaTeX is likely to occur. So that's what I mean, that when you do these things at scale, you only have a few chances. So I think moving forward, we'll have like much clearer definitions of, here's how we're filtering the data, and we don't want to just do it for math. We want to like filter for, this specific subset of biology or something like that. That's kind of where I see things going.
Laura, please. Yeah, the next speaker can rotate.
Yeah. So for the supervision on the intermediate steps, yeah, that's a great idea, and it's actually the key part of the evaluation method. So I didn't provide many details, but what we actually do is you get supervision on each intermediate step of a solution. This could be from human annotators, or more and more people are trying to look into just getting these automatically. And then, yeah, getting this intermediate supervision turns out to be just as useful or complementary to getting supervision on the output. And then the other question, I already forgot. Oh, the accuracy, yeah. Yeah. Yeah, exactly. So I think one way to think about these is to look at what the data is. So the math benchmark is based on high school level competition problems. And so if a model gets 50%, then you could look at the level of the different problems, and you could have some sense of like, okay, maybe this model is like decent at these kind of types of high school level math.
All right, let's.
Another question. Am I allowed to ask, or?
Actually, I think it's good if you catch him over the break.
Okay, that's fine.
Yeah, thank you very much. Sorry, but thank you very much, Sean, for a great talk.